we're going to start Unit 4 today. And so Unit 4 is the probability section of the probability and statistics. And so Unit 4 involves Chapter 14, 15, 16, and 17. 14 is just introduction to probability, and so you'll be able to do most of the problems because you've done them before. Middle school, Mr. Scott's class, not too complicated. Chapter 15, we go into more complex probabilities. We talk about what happens when there's no replacement. We talk about what's happening with tree diagrams and with Venn diagrams, just more complex ideas. And then in Chapter 16 and 17, we're going to address some things that maybe you haven't learned before. So Unit 4 will last us the rest of the semester. But again, we're starting with Chapter 14. It's not that bad. Okay? So first, just some general ideas. Okay? In this case, the chapter, always has an example they use. And so the example we're talking about is the color of the light, like the traffic light, completely unpredictable. So if you're driving the same way to school every day and there's a traffic light, and you want to see how often you get a green light, okay? Well, then you can create a model just like this, where you have a cumulative percentage. All right, that means they're going to add up the percentage and average it out over time. All right? So if you look at this graph, it has day number and percent of the time it was green. So the first day, you have 100% green. That means it must have been green that day. Then the next day, it averages out to 50% green, so it must not have been green that day. And then you can see it spikes up and down, and then over time, it looks like it's evening itself out. All right? Then it's approaching approximately 35% is what our book is saying. All right? So we know that stoplights, green and red, are going to be more often than yellow, because yellow is just kind of a warning. But so they're saying that this light in particular is green 35% of the time. Okay? Well, just some vocabulary really quickly. Each time we would approach that light, that would be a trial. Every occasion when we observe some random event. So we're thinking about the traffic light as a random event. Every time we approach it, that would be a trial. And then every time we recorded what happened, that would be an outcome. So was it green? Was it yellow? Was it red? That's an outcome. Then we start combining outcomes. So like over time, we say that we have an event. What's the probability of getting a green light? That's an event, right? Because it's been tested over several different days, different trials, with several different outcomes. Then the possible outcomes are going to be the sample space, and we'll do some practice sample spaces today. But that's, again, all possible outcomes. So we've talked about those things before, okay? But the idea that over time, the probability is going to average itself out, like with the green light scenario, is due to the law of large numbers, okay? If we assume that the events are independent, so that means that the outcome of one trial doesn't affect the outcomes of the others. So we're going to say that going to the light each day is an independent event. Okay? Then as the number of trials increases, the long run relative frequency, which remember is just a fancy name for percentage, so the long run percentage gets closer and closer to a single value. So we saw that in this graph, that over time, we get closer and closer to just leveling out at 35%. So that allows us to actually come up with the definition of a probability. So because the percentages settle down, that's how we get a probability. That's how we know that when you roll a die, 1 out of 6 times you're going to get a 1. Yes, there's 6 spaces and there's 1 outcome, but that's been tested and tried over and over and over again. If you keep rolling and keep rolling and keep rolling, then the probability you get a 1 is 1/6. Okay? So that's where the definition of probability comes from. Now, there is the law of large numbers, but there's also what people refer to as the law of averages, which is not a statistical thing. All right? That's why it says it's non-existent. Okay? And it's because of the idea of the long run. People think that an event that hasn't occurred in a while, that the outcome of an event hasn't occurred, is due up. We use this a lot in sports. We say, oh, this guy is due for a home run. Well, any time that person's at bat, they could get a home run. It's not as likely as maybe a hit or a strike, but any time they have to bat, they could get a home run. And so what happens is if you don't get a home run and you don't get a home run and you get a home run, people start saying that you're due up for a home run. All right? That's not likely because you haven't gotten a home run that you're due up for one sooner rather than later. You could again hit one any single time you're up to bat. So we call it the law of averages because people are determining this based on short run behavior instead of on the actual long run. If you're talking about probabilities, you base that on long spread out number of trials. When people are talking about he's due up for a home run, you're only talking about maybe 7, 8, 9, 10 trials, times you're up to bat, and he's due up, he's due up, he's due up. He could get a home run at any given time. So be careful of the law of averages. We're not due for anything. Right? Anything could happen at any individual time. So some quick, and we spent a short amount of time on this today, so some quick intro questions, and I'll give you the assignment. The first one is just about sample spaces. So for each of the following, list the sample space and tell whether you think the events are equally likely. So again, the sample space is just a list of all the possible outcomes. So A says toss 2 coins and record the order of heads and tails. So we're definitely tossing 2 coins and recording the order. Well, I could get heads on both, and I could get tails on both. And this is recording the order, then I could get heads, then tails, or I could get tails, then heads. Those are the 4 possible outcomes, so that's the sample space. Are these equally likely to occur? Yes. All right. 1 penny or 1 coin is not dependent on the other, so they're completely independent of each other, and so they don't affect the outcome of the other coin, and so we would say that any of these are equally likely to occur. A family has 3 children. Record the number of boys. Well, you might have 0 boys, 1 boy, 2 boys, or 3 boys. That's the sample space. Are all of these equally likely? When we start getting into families and genetics, it's probably not equally likely. All right? That's hard to determine, though. So generally in our class, they'll say, assume this is equally likely, but it isn't technically. On C, flip a coin until you get a head or 3 consecutive tails and record each flip. So flipping a coin until one of these 2 things happens. So we could flip the coin and we get heads. Well, if we get heads, we stop. So we're done. If we didn't get heads, and then we get tails, right? And then on the next coin, we get heads, and we would stop. Well, if that didn't happen, that means we get tails, and then we could get heads, but then that means we stop. But if we didn't get heads, we get tails, and tails, and then it says 3 consecutive tails, we stop. So that's the possible outcomes. Are these equally likely? The answer is no, because you're basing, if you're going to flip again, on the first flip. So if you flipped heads, that's 50% chance. But now if you get tails, then you're going to flip again. You have 2 events that are related to each other, and they're going to affect the outcomes. So they're not independent. So you're going to not have equally likely events. And then roll 2 dice and record the larger number. Well, if you have 2 dice, you have 1 through 6. You could roll 2 ones. So 1 could be the largest number. 2 could be larger than 1, right? 3 could be larger than 1 and 2. And then 4, 5. All of these are possibilities to be the larger number. Are they equally likely? No. 4 is much more likely to be the larger number than 1 is, because 4 is larger than 1, 2, and 3. But 1 is only, quote unquote, larger than 1. All right, so these are not equally likely to occur. Questions about sample spaces. You're just listing out the possible outcomes and determining if they're equally likely. All right. So it says a casino claims that its roulette wheel is truly random. And so what should that mean? We talked about this before in chapter 11. So truly random means you shouldn't be able to predict what's happening next. Oh, of course, we could always guess what's going to happen. But that doesn't count. We're just saying we shouldn't be able to predict what's happening next. We shouldn't know the next outcome. And then the last question here, comment on the following. What I think is our best determination is it will be a colder than normal winter, said Pamela Knox, a Wisconsin state climatologist. I'm basing that on a couple of different things. First, in looking at the past few winters, there has been a lack of really cold weather. Even though we are not supposed to use the law of averages, we are due. Well, I'm going to comment on this. She's a climatologist, which means that should be her specialty is the weather. And the first thing she's basing her decision on is the law of averages, which she says that she knows you're not supposed to use. All right, she's basing this on the past few winters. Remember, we base probabilities on what's happening in the long run. So that's short term. We can't use that. So I'm concerned that the climatologist is using that as her reasoning when maybe she should be using some other weather speak or something. Okay? So when it says comment, you're just kind of dissecting it. Law of averages is bad. She says it's bad. We shouldn't have used it, but that's what she's talking about. Okay? Well, this is a good intro, so I'll give you the assignment. It's not very long. And then tomorrow we're actually going to calculate probabilities.